Hello and welcome to another session of Introduction to Astrophysical Fluids. In this session, we will discuss a very small topic, although very interesting, that is the topic of Elsasser variables. Okay, so in the year 1950, Elsasser wrote this whole set of MHD equations, mostly for, for incompressible MHD equations in terms of Elsasser variables. Okay, and that specific style of writing actually revealed a number of very interesting facts and features of MHD which we cannot see in general when we write the equation in terms of V and B. So if you remember that the incompressible MHD, for example, so the key variables are simply V and B, because rho is a constant, the density, fluid density is constant. Okay, so simply we can write the whole thing in terms of V and B. Of course, we have pressure, we have a pressure like variable, but we also know from our previous discussion that finally pressure can be solved in terms of velocity. And so finally the message is that in order to construct a dynamical theory, we simply need only V and B. Okay, and when the fluid is incompressible, okay, so incompressible MHD means that the fluid is incompressible. That means the divergence of V, that is the divergence of the fluid velocity, is 0. And we also know that the divergence of B is nothing but capital B by root over mu 0 rho. Okay, so if rho is, so let's say this quantity, and mu 0 is a constant, sorry, not rho 0 but rho, and rho is a constant, so the divergence of B, small b, is nothing but equivalent to some constant times divergence of B0, and divergence of B0 is always 0. So this will also be divergence less vector, the small v and small b. Now we can write the two basic equations of incompressible MHD as this. The first one is the momentum evolution equation. So del V del T plus V dot nabla V is equal to minus gradient of P by rho plus curl of B cross B by mu 0 rho. Okay, so that is the Lorentz force term we have already seen. Here we are just neglecting the forcing term because in the original work of Elsasser in 1950, he also neglected the forcing term. But I mean, if you include the forcing term, that does not change any big thing, because forcing term is in general independent of the force, of the fluid fields like V and B. Okay, so because this is an external forcing term. However, here we just omit that and we write this, the right hand side, as the pressure gradient force, Lorentz force, and the viscous force, which is eta times, nu times Laplacian V or Nabla square V. Okay. Now, this equation, so this term is kept intact. This term can be now written as curl of small b cross small b, because when every capital B is just divided by root over mu 0 rho, it gives one small b. So it will have simply this total equation will have the simple expression as curl of small b cross small b plus again the viscous term, and then this one, by using the famous vector identity, you can write this one is equal to minus gradient of b square by 2 plus b dot nabla b. So this treatment we have already seen when we introduced magnetic pressure and magnetic tension right from Lorentz force. Okay, so now if we simply see the equation, it should look like del v del t plus v dot nabla v is equal to minus gradient of P by rho minus, where rho is a constant, minus nabla B square by 2 or gradient of B square by 2 plus B dot nabla B plus nu times Laplacian V. Okay. And what about the equation for the magnetic field evolution? So that we can actually write del B del T, capital B, del B del T is equal to, so if you just remember the equation, it should look like this. Del B del T is equal to curl of V cross B plus eta Laplacian B. Now we just divide both sides, okay, by, we just divide both sides by root over mu 0 rho, so this side as well. So and then finally you have this del small b del T is equal to minus, so this will be simply then this will be curl of V cross small b plus eta nabla square small b. Okay, so this one is this, and this one, when you expand, you will get two terms like this. So del B del T is nothing but is equal to minus V dot nabla B plus B dot nabla V plus eta Laplacian B. So you see, here we have the equation for both V and B. Both are divergence-less, and the evolution equation of both includes only terms like B dot nabla B, B dot nabla V, V dot nabla V, V dot nabla B, and this gradient type of term. Okay, this is also a pure gradient here because rho is a constant. Okay, Elsasser just observed this thing and he just once again wrote this equation as this: del V del T is equal to minus V dot nabla V minus gradient of P plus B dot nabla B minus gradient of PB, that is the magnetic pressure, plus nu times Laplacian V. Laplacian means the nabla square. Okay, and here he just said that the constant density is now normalized to unity 1. So we just don't write any longer the rho over here. Okay, we don't need. And then we write del B del T is equal to minus V dot nabla B plus B dot nabla V plus eta times nabla square or Laplacian B. Okay, so and finally he had this too. Then he actually wrote the whole equation, the set of two equations by redefining a new set of variables called the Elsasser variables, which are nothing but V plus minus small b, right? So both of them are of dimension of velocity, so Elsasser variables are of the dimension of velocity. Okay, so Z plus is nothing but V plus small b, and Z minus is nothing but V minus small b. Okay, now if you just add capital A and capital B, you will get the equation for Z plus, and you will simply write del Z plus del T is equal to minus Z minus dot nabla Z plus minus gradient of P total, which is P plus PB, plus the viscous term, which is written in a fancy way. And for del T of Z minus, we have is equal to minus Z plus dot nabla Z minus minus gradient of P total plus this total dissipation term. Now this dissipation terms are written in a way so that this remains some, carries some symmetry. So this is nothing but just writing. So like in this equation you will have the dissipation contribution like this: eta V plus nu lambda nabla square V plus eta nabla square B. So we just say this one is equal to d plus z plus d minus z minus, of course here this sign they are exactly equal to lambda squares, and then you just write v is equal to, so if z plus minus are v plus b and v minus b respectively, then v will be simply equal to z plus z minus by 2, and b will be equal to z plus minus z minus by 2. So if you just simply write v and b as z plus z minus by 2, and here like z plus minus z minus by 2, then you are done. Then you can actually find d plus and d minus in terms of eta and nu. Okay, and I mean this is simply a two-step calculation, so I rather ask you to do. Now the interesting thing is that now we have the evolution equation for two variables, which are the Elsasser variables z plus and z minus. So for z plus, you see that the advective term contains z minus, and z minus, the advective term contains z plus. So neither z plus nor z minus can self-advect. Okay, so z plus is advected by z minus and z minus is advected by z plus. And for both the variables, the pressure is nothing but the equivalent pressure, fluid pressure is nothing but the total pressure, which is the sum of the fluid pressure and the magnetic pressure. Okay, this specific writing is particularly interesting when we will talk about MHD turbulence, okay, and the phenomenology of Krishnel-Iroshnikov. Okay, now one simple thing is that here you know that this is the definition. So can you now write this two quantities, like let's say I can just write half v square. So if it is incompressible MHD and rho is 1, then the total energy density is nothing but v square by 2 plus b square by 2, because density rho is equal to 1, right? And then what will be this in terms of the Elsasser variables? Well, can you write that? So v square plus b square by 2. So simply it will be half v square plus b square, and v square is nothing but z plus z minus by 2 whole square plus z plus minus z minus by 2 whole square. Okay, and what is this? So this is nothing but, so that will be exactly equal to half of so a plus b whole square plus, I'm sorry, maybe I have to just I have to change the writing part, sorry. So that will be equal to half of so this is a plus b whole square. So first I take 1 4 factor common, so that will make it 8, and inside this it will be 2 times z plus square plus z minus square. So z plus square plus z minus square. So it will be simply 1 by 4 z plus square plus z minus square. Okay, so that is the expression of the total energy density in terms of z plus and z minus. In the same way, you can also express the cross helicity density in terms of the Elsasser variables. How? So v is z plus z minus by 2, and this one will be z plus minus z minus by 2, and then you multiply, and you know better than me what would be the expression. Okay, so it will be 1 by 4 z plus square minus z minus square. Okay, so now the thing is that you have seen that 1 by 4 z plus square plus z minus square is something which is the density of a conserved quantity. And also you have seen that 1 by 4 z plus square minus z minus square is something which is the density of something which is conserved. That is the cross helicity part. If both are conserved, then the sum of the two will be conserved and the subtraction of the two will be conserved, right? Will be the density of some conserved quantities. And that's why you can actually say that both the z plus square and z minus square will correspond to the densities of two conserved quantities. Okay, and they are known as pseudo energies. Okay, so all these things are there. So Elsasser variables are very interesting for several cases, and mostly so historically what Elsasser did was to write the incompressible MHD equations in terms of his variables. But after that, later Marsh and Mangini in the year 1987, which is 37 years later, they used this Elsasser variables. They tried to write the compressible MHD equations for polytropic fluid, MHD fluid, in terms of compressible Elsasser variables. That means, so the Elsasser variables are having the same definition, but your rho is no longer changing now. Okay, so it doesn't have a very symmetric form, but still it can be written. And this writing actually specifically is very interesting for compressible MHD turbulence as well. Okay, so from the next lecture we will start discussing another interesting aspect of MHD, that is the linear wave modes. Okay, thank you very much.